till now whatever problems we have solved, you have seen that the range of those independent variables x, t like that were lying either from 0 to infinity or from minus infinity to infinity. But in real life physical problems, sometimes it may happen that they have some finite values, that is it may lies from say 2 to 10 or it may lies from 0 to pi, or the range is from 0 to some finite value n, like that way. So, whenever I have the finite range for independent variables, I cannot use the directly the transform techniques, especially the Fourier or Laplace techniques directly. So, I have to think for something else for the real life physical problems, where the independent variables varies in a finite range. For that, we will now study the finite Fourier transform. So, in many boundary value problems of practical importance are governed by the equations which are defined in finite intervals, as I was mentioning. This is one of the main reason for finite Fourier transform. So, Fourier transform method is extended to problems with finite range for independent variables. So, please note this one, that Fourier transform method whatever we have done earlier, that will be extended to the problems where the independent variable lies in a finite range. And the inverse Fourier transform of such functions can be found by the use of Fourier series, that we will tell you. So, we are saying that Fourier transform method will be extended to the problems with a finite range for independent variables, whereas inverse Fourier transform of such functions can be found by the use of Fourier series. So, if you see here, if you recall, I am just mentioning, if a function f x satisfies the Dirichlet's condition in 0 to pi, then the corresponding Fourier sine series will be, I am just quickly I will tell it, Fourier sine series will be equals to f x equals summation n equals 1 to infinity b n into sin n x. This we have done earlier, that if f x satisfies the Dirichlet's conditions in 0 to pi, corresponding Fourier sine series function of f x will be equals to this summation n equals 1 to infinity b n sin n x, where your b n is equals to, if you remember, 2 by pi 0 to pi f x into sin n x dx. Your n varies from 1 to like this. So, this is equation 2, and Fourier series for this Fourier series 1 converges to f x at all points, converges to, please note, Fourier series 1 converges to f x at all points where f x is continuous, and if you recall, it converges to this value half into f of x plus 0 plus f of x minus 0 at the point of discontinuity, right. So, the Fourier series of this one converges to f x at all points wherever your function, where it is continuous. If it is discontinuous, then it converges to half of f x plus 0 plus f of x minus 0 wherever it is discontinuous. So, that you can write down, and so therefore, whatever we have told is your f x is equals to summation n equals 1 to infinity b n sin n x, where b n is 2 by pi 0 to pi f x sin n x dx, and Fourier series 1 converges to f x at all points where f x is continuous, and it converges to half into f of x plus 0 plus f of x minus 0 at the point of discontinuities. So, therefore, this is the Fourier sine series of a function which is defined by 1 and the coefficient Bn is defined by 2. Similarly, Fourier cosine series of f x, please note that whatever we are defining it in 0 to pi. So, corresponding Fourier cosine series. So, now I am saying Fourier cosine series, please note this. Earlier one was Fourier sine series. So, it can be written as f x equals a 0 by 2 plus summation n equals 1 to infinity a n into cos n x. So, this is equation 3, where your a naught is equals to 2 by pi 0 to pi f x dx. All these things we have done earlier, and a n equals 2 by pi 0 to pi f x cos n x dx. Again n equals 1, 2, 3 like this. So, say this is equation 4. So, please recall this, because as we have told, whenever I will try to find out inverse Fourier finite transform, then I will use this particular series. Using this only I can obtain those values. So, Fourier cosine transform is defined by equation 3, where a naught and a n, the coefficients, are defined by equation 4. So, by this way, once I am writing this one, the corresponding Fourier cosine form is this, where a naught is this and a n is this. So, now let us come to the finite Fourier sine transform. Let a function f x satisfies Dirichlet's condition in 0 to pi. Then please note this one, function f x satisfies Dirichlet's condition in 0 to pi. Whenever we have done the Fourier series, then we have defined this Dirichlet's condition. So, I am not stating here. Then the finite sine transform of f x, please note this, finite sine transform of f x is defined as f x, this is equals to f s n I am defining, and this is equals 0 to pi f x sin n x dx, where n varies 1, 2, 3 like this way. So, this is equation 5. So, if you compare equation 2 and equation 5, please see, your equation 2 was b n equals, your equation 2 was b n equals 2 by pi 0 to pi f x into sin n x dx. This was your equation 2. So, if I compare this equation 2 and equation 5, then I can write down b n equals nothing but 2 by pi into Fourier sine transform of n, where n varies 1, 2, 3 like this way. So, this is the this one. So, therefore, Fourier sine transform of f x, this is equals to, we are defining as Fourier sine transform of f x equals capital F s of n. This is equals 0 to pi f x sin n x dx. So, finite Fourier sine transform of f x is equals to 0 to pi f x sin n x dx, n varies from 1, 2, 3 like this. And from these two we can tell that b n is nothing but 2 by pi into Fourier sine transform of n. And similarly, the inverse, let me write down, inverse finite sine transform. Inverse finite sine transform can be defined as like this of f s n, obviously this is equals to will be f x, and this is nothing but the formula which we got earlier, the series, that is summation n equals 1 to infinity. It was b n, and b n we have shown it nothing but Fsn into sin nx. This is your 7. So, please note that inverse Fourier sine transform we are defining in terms of Fourier series earlier, where we defined f x equals 2 by pi summation n equals 1 to infinity b n sin n x, where just now we have shown b n equals f s n. Therefore, Fourier sine inverse of f s n equals f x, and this equals 2 by pi summation n equals 1 to infinity f s n into sin n x. And if the independent variable, this is the independent variable x, lies in the interval say 0 to L, that is any general interval, this whatever we have talked about, that is if it lies in 0 to pi. But if it lies any interval 0 to L, in that case we define like this: Fourier sine transform of f x, this is equals to f s n, same line as we have done it for this. This will be 0 to L f x into sin n pi x by L. Please note this one. This again we have done how n pi x by L came earlier, n equals 1 2 like this. So, and your inverse Fourier sine transform, that is Fourier inverse of f s n, which is nothing but f x, this is equals to 2 by L summation n equals 1 to infinity f s n into sin n pi x by L, and n varies as we have told, n equals 1 to infinity. So, please note this one: for inverse Fourier sine transform, Fourier sine inverse is 2 by pi summation n equals 1 to infinity f s n into sin n pi x, and whatever we have defined, that is for 0 to pi, if x values lies in 0 to pi, but x may lie in some interval 0 to a. So, whenever x lies in 0 to L, in that case Fourier sine inverse of f x will be 0 to L f x sin n pi x by L dx, n varies from 1 to this, and Fourier sine inverse of f s n equals f x. This will be equals to 2 by L summation n equals 1 to infinity f s n into sin n pi x by L. So, just see it quickly here. The finite sine transform we are defining as 0 to pi f x sin n x dx, and if I compare 2 with 5, I can tell that b n equals 2 by 5 f s n. Already I have explained what is equation 2. So, by comparing 2 and 5, we can tell b n is this quantity. So, inverse Fourier sine transform is defined as Fourier sine inverse of capital F s n, which is equals to nothing but f x, and f x is what? The Fourier sine series whatever we have defined. 2 by pi sin summation n equals 1 to infinity b n into sin n x was there, b n as we have told, it will be replaced by f s n. So, you will get this thing. When the independent variable x lies in the interval 0 to L, then the finite sine series can be defined as, the only change will be in the earlier case it was defined in 0 to pi, therefore, integration was from 0 to pi. In this case, it will be integration will be from 0 to L f x, and this sine coefficient will be changed to sin n pi x by L into dx, and the inverse function f x can be defined as 2 by L summation n equals 1 to infinity f s n into sin n pi x by L. On the same way, we can define the finite Fourier cosine transform, and this we can define as like this. The finite cosine transform of f x is Fourier cosine transform of n equals 0 to pi f x cos n x dx, n varies from 0 1 2, only change here n is from 0 1 2, for Fourier sine case it was n equals 1 2 3 like this, and the inverse Fourier cosine transform is defined as f x equals f c 0 by pi, here it will be f c 0 by pi plus 2 by pi summation n equals 1 to infinity fcn into cos nx, which holds at each point in 0 to pi where fx is continuous. So, fc0 and fcn came in the same way as we have discussed for the case of Fourier sine transform. And when the independent variable x lies in 0 to L, the only change will be 0 to L, limit of the integration is from 0 to L. So, that fx cos n pi x by L, and this is n equals 0, 1, 2 like this, and Fourier sine transform of Fourier inverse Fourier cosine transform will be fx equals fc0 by L plus 2 by L summation n equals 1 to infinity fcn into cos n pi x by L. So, by this way we are defining Fourier sine transform, Fourier finite sine transform and finite cosine transform. Now, let us see the finite transform of derivatives. Whenever we want to find out the solution of second order ODEs, so I have to find out the finite transform of derivatives. So, finite transform of derivatives for that one, number 1, the function f of x t is there, x lies between 0 to L I am assuming, and t is greater than 0. So, I want to find out the finite transform of derivatives of f of x t, where x lies between 0 to L and t is greater than 0. Number 1, finite sine transform of del f del x. From the definition, finite sine transform of del f del x 0 to L function is del f del x into sin n pi x by L into dx. So, if you use integration by parts, then you will obtain first part will be f of x t into sin n pi x by L, limit is from 0 to L, minus n pi by L into 0 to L f of x t into cos of n pi x by L into dx. After integration, I am getting this derivative n pi by L. Now, this part will be vanishing at this one, both at 0 and both at L, it will be vanishing. So, this part will not be there, and this will be equals to minus n pi by L 0 to L f of x t into cos of n pi x by L into dx, and 0 to L. So, whenever you are writing 0 to L f of x t into cos n pi x by L dx, this is nothing but Fourier finite Fourier cosine transform of f x t. So, that this equals, you can write down minus n pi by L into finite Fourier cosine transform of this f of x t, and this equals, you can write down minus n pi by L into capital F of c of n. So, therefore, Fourier sine transform of del f del x, Fourier sine transform of del f del x is nothing but minus n pi by L into Fourier cosine transform of n, that is Fourier cosine transform of f of x t. So, if I see here, the Fourier sine transform of del x equals 0 to L del f del x into sin n pi x by L. If I use integration by parts, then I will get two terms. The first term, whenever we will put the limits 0 and L, the term will vanish. So, that you will have only this thing, and this is nothing but the integration is Fourier cosine transform, finite Fourier cosine transform of f x t. So, we are writing this, and ultimately we are writing as Fourier minus n pi x n pi by L into Fourier finite Fourier cosine transform of f of finite Fourier cosine transform of f of x t. The second one is the Fourier cosine transform of del f del x. Fourier cosine transform of del f del x. This is equals to 0 to L del f del x into cos of n pi x by L into dx. From definition I can tell this is equals to again by integration by parts f of x t into cos of n pi x by L 0 to L, x lies between 0 to L plus n pi by L will come 0 to L f of x t into sine of n pi x by L into dx. This term will vanish as usual for limiting values 0 and L. So, that you will get n pi by L into this is sorry, here it will not be 0 because at L equals 0 this is not vanishing. At x equals 0 this is x equals 0, this will not vanish. At x equals 0 it is cos n pi, that will also not vanish. It depends on the value of this one. So, I am just writing this. This will be equals to n pi by L into 0 to L f x sin n pi x by L dx is nothing but finite Fourier sine transform of f x. So, that you can write down this as finite Fourier sine transform of f of x t minus, if I put the lower limit will be f of 0 t, this part is 1. So, f of 0 t minus f of L t into cos n pi. I will come to this, means whenever I want to use Fourier cosine finite Fourier cosine transform, I need to know the value of f of 0 t, f of L t like this, otherwise I cannot evaluate this thing. So, if I go on quickly on this one, this is equals to, you are getting this, and if I put the values, I will obtain n pi by L into Fourier finite Fourier sine transform of f of x t minus the limiting value of this, that will not be vanishing, f of 0 t minus f of L t into cos n pi. Let us see the number 3, that is Fourier sine transform of del to f del x square. Fourier sine transform of del to f del x square. This is equals to 0 to L del to f del x square into sin n pi x by L sin n pi x by L into dx. So, first part will be equals to del f del x into sin n pi x by L, x is from 0 to L, minus n pi by L into 0 to L del f del x into cos of n pi x by L into dx. So, this part will become only this part here, again it will vanish. So, this part will be minus n pi by L, again use integration by parts. If I use integration by parts, minus n pi by L will be coming here, f of x t into cos of n pi x by L, limiting value is from 0 to L plus n pi by L into 0 to L. Now, it is becoming f of x t into sine of n pi x by L into dx. And this integral minus n pi by L I can take common, minus n pi by L I can take common over here. If I take common minus n pi by L over here, then this part will be, this part minus n pi by L is here, and this case this is one is common. So, minus n pi by L. So, the second integral is n pi by L into finite Fourier sine transform of f of x t. So, that this is finite Fourier sine transform of f x minus this will become f of 0 t, because this will not be cancelled, f of 0 t minus f of L t into cos n pi. So, therefore, Fourier sine transform of del square del square f del x square equals minus n pi by L into n pi by L Fourier sine transform of f x minus f of 0 t by putting the limiting value f of 0 t minus f of L t into cos n pi. This will be vanishing. So, if I use this Fourier sine transform of this by integration by parts, then again the first part here is 0. So, the second integral again I am using integration by parts, so that you will get two terms, and if you evaluate the integral is nothing but n pi by L into Fourier sine transform of f x minus f 0 t minus f L t into cos n pi. So, I have to remember these things. Now, on the same way you are getting the Fourier sine transform of del square minus del f x square equals this. As a special case, if I consider f 0 t equals f L t equals 0, that is at the point x equals 0, at the point x equals L, the value of the function is 0. In that case, Fourier sine transform of del 2 f del x square will be simply reduced to minus n square pi square by L square into Fourier sine transform of f of x t. On the same way, if you proceed, then you will find that Fourier cosine transform of del 2 f del x square, if you process similarly, will be minus n square pi square by L square into Fourier cosine transform of f of x t minus f x 0 t minus f x L t into cos n pi. This I am not showing you, because if you follow the method which we have used for finding Fourier sine transform of finite Fourier sine transform of del 2 f del x square, in the same way you will get this particular equation. In case del f del x vanishes at the end points at x equals 0 and at x equals L, just like we have done as a special case for finite Fourier sine transform. So, if del f del x vanishes at x equals 0 and at x equals n, then finite Fourier cosine transform of del 2 f del x square will be reduced to minus n square pi square by L square into finite Fourier cosine transform of f of x t. So, these four formulas are very much required, and you have to be you should remember it or you should derive it, so that whenever we will try to solve the problems, then we can use these particular formulas and we can solve the problems on finite Fourier transforms.